FEM is used for elliptical differential equations because they are boundary value problems. And parabolic and hyperbolic, they are like initial value problems. So we are generally using FEM with FDM to convert them into algebraic equations. And why it is happening? Because in case of parabolic and hyperbolic situation, it's a initial value problem, means time is going to be there as a parameter, as independent parameter. And when time is there as independent parameter, and if you create differential equation, you will get temporal derivative also, time derivative also. And FEM is not able to convert that thing into algebraic part. That is why we require FDM also to convert that temporal part into algebraic, and then other parameters you are converting through FEM. So we are using single FEM also and combination also. So this differential equation is generally available. Any physical system can be converted into differential equation. If I am waving my hand like this can be converted into a second order differential equation. Because I am stopping my hand, then again moving it, it means acceleration is involved, and acceleration is nothing but second differentiation of displacement. So it's a second order differential equation. So whatever is happening physically can be converted into differential equation, and then through FEM we can solve it. That is one path. Another path is through Fourier transform we can convert it into system matrix, and with eigenvalue problems and solution approach we can convert into modal parameters. And modal parameters means natural frequency, mode shapes, and damping factors. So we are getting those things. This is called analytical way of doing modal analysis. Second path, we are having FRF, frequency response functions, that is a response model, and through curve fitting we are getting modal parameters. Either directly from frequency response we can do it, or we can have time response model, impulse responses, and then through curve fitting we are getting modal parameters. So we can get modal parameters, that is frequency, damping factors, and mode shapes from frequency response as well as from time response. This is called experimental. So what we are doing, we are generally using an FFT. FFT is recording the things in impulse, then we are converting into FRF, and then we are doing a curve fitting, and we are getting the natural frequencies, mode shapes, and damping factors. So this is how we are doing experimental modal analysis. Here we are doing analytical modal analysis. Let's see single degree of freedom system. This is again experimental thing. This is the structure, a simple beam. This we are taking the response. This is the input. We are hitting this structure with this hammer. So one wire is coming from this. This is another wire. So we are applying an impulse, and then we are getting this response. We are converting this time domain response into frequency domain response. This is FRF, frequency response function, and then the curve fitting, and finally the modal parameters. So this is another way of representing experimental modal analysis. Now theoretical modal analysis, we have got single degree of freedom system, multi-degree of freedom system, both in time domain, frequency domain, but I am going to drive equations in frequency domain. That is much popular and like available in all the books. So I'm going to apply frequency domain approach for modal analysis. I am like switching over 2-3 slides quickly because they are not important. They are going to come again once we will understand the mathematics of modal analysis. So if you take any free undamped system means a mass is hanging with a spring. So a spring is there and mass is there. Only two properties. K is stiffness, which is the property of a spring. M, mass, which is the property of mass. And generally when you take any structure, you have mass of that structure and you have also stiffness of that structure. So these are the two things. Generally third property right now we are not talking about, that is damping. Because right now we are talking of free undamped vibrations or free undamped system. Once we will switch over to damped, then the third element will also pop up, and that is the damping. We may have viscous damping, we may have structural damping, we may have frictional damping. But this case is related to free undamped. Mx double dot plus kx is equal to 0. So this is the mass, this is the acceleration. Together it is inertia force plus this is a stiffness multiplied by displacement. Together it is again force, because k into x is a spring force, mx double dot is inertia force. And we are not applying any force. It means it is free vibration. So mx double dot plus kx is equal to 0 is the equation of motion or system, conversion of physical system into mathematics. Once this mathematics is available, it's a differential equation. Now we have to solve it. The possible or trial solution we are taking, that x in time domain is equal to x in frequency domain. This omega is frequency in radian per second. You may have in hertz also. So this small x within bracket t is time related thing, is converted into frequency related thing. And as soon as we put this, we substitute this equation into this very first, we are going to get k minus omega square m is equal to 0. And it may lead to omega 0, which is the natural frequency, is equal to under root k by m. So natural frequency is equal to under root k by m, we are getting from free undamped system. And that is why we are calling it as a natural frequency. Natural means no external force is applied, only the system is disturbed once, एक बारी disturb किया उसको, and you are having k, you are having m, k by m taking under root is going to tell you that this is the natural frequency of this system. And because the system is only single degree of freedom, it is only going to have single natural frequency. If the system is of 2 degree of freedom, it will have 2 natural frequency. If it is 3 degree of freedom, it will have 3 natural frequencies. If it is multi-degree of freedom, 5, 6, 1, 10,000, 1 lakh, it will have that much of number of frequencies. And then mode shapes also, because mode shape is a vector. So related to each natural frequency, you are going to get a mode shape. So if suppose it is a single degree of freedom, 1 natural frequency and 1 mode shape vector. If it is 2 degree of freedom, 2 frequencies and 2 different mode shape vectors. One related to omega 1, another one related to omega 2. If you make it force, suppose this time you are not taking this side 0, this side you are not taking 0, this side you are taking a force. And that force is also time dependent. But as we have converted time into frequency, for displacement as well as force, we are going to get this equation. K minus omega square m within bracket, then x e I omega t is equal to f e I omega t. This is conversion of force and this is conversion of x. If you look at the previous slide, here we are having x. So we are not saying that x is equal to 0. We are saying k minus omega square m is equal to 0. Because if we make x is equal to 0, there will not be any vibration. So x will never be equal to 0, but k minus omega square m can be 0. And from that only we have calculated that omega square is equal to k by m, or omega is equal to under root k by m. In this case, that x we have converted into x ei omega t, and f we have converted into f I omega t. And if we take ratio of these two, x upon f, automatically this I omega t is going to be vanished. So we will get x upon f, and this x upon f is nothing but 1 upon k minus omega square m. This is called FRF, frequency response function. You can represent it as alpha omega, or you can represent it as h omega. Both are like applicable. So try to remember this thing, because this formula is going to become different every time. As soon as you change the boundary condition and system property, it will change. Like right now it is forced undamped system. So you are having only k and you are having only m. There is no viscous component into it. And this x means displacement divided by force. This thing is called frequency response function. It is denoted by alpha omega, and it is given by 1 upon k minus omega square m. And if you plot this, you give k, if it is a single degree of freedom, give k, give m, and plot it for different frequencies. You will get the frequency response functions. Let me show you one figure. This is generally the 3-dimensional figure. This line is coming here and then going like this. If you project this whole thing, dark thing, onto this plane, you will get this shape, this lower dip. And if you project it from the top view, you will get this shape on the bottom plane. So this is front plane, say this is bottom plane, and this is side plane. These are the different representation of FRF in 2 dimension. In 3 dimension, it is simply like this. We have got imaginary part, we have got real part, and we have got frequency part. So if you look at this, this is the receptance, means FRF. There are 3 types of FRFs. I will tell you that also. But this is real part and this is imaginary part. Go back to this. This is the imaginary part, this lower dip, and this going up and then directly coming down. This is real part. So this is real part. Sorry, this is this is real part, and this lower dip is imaginary part. So these are two graphs which I have extracted from this only. And if you want to represent FRF in terms of phase and magnitude, this is the magnitude and this is the phase. If you look at the magnitude, you will find a sharp peak and then zero, almost zero vibration. This sharp peak represents that this is the resonant frequency, because resonance definition says that whenever the applied frequency matches with the natural frequency of the system, the whole system vibrate significantly. So this is like very high. This high peak amplitude of this level is an indication that 20 hertz or 20 hertz is 20 or like say 19 when you are getting a peak. So this 19 hertz is the natural frequency of the system. And if you are knowing the natural frequency of the system, you will always try to design it in such a way, means not designing, you are always try to apply loads in such a way that the applied load frequency may not match with the natural frequency of the system, because if it is going to match, it is going to vibrate. So we have to avoid this situation. That is why we must know the natural frequencies, its phase, its amplitude, its real part, its imaginary part. Now we are putting damping also into it. Earlier we have taken stiffness, mass only, now damping also. As soon as you put damping, that equation, same equation, if you look at this equation, only one equation you have to remember, this one, K minus omega square m outside x e I omega t f e I omega t. If you include damping term also, automatically in case of damping, the equation will become, I have directly written this equation, but the equation will be mx double dot plus c omega, mx double dot plus cx dot plus kx is equal to f. That is the basic equation. Mx double dot is the inertia force, plus cx dot is the damping force, plus kx is the spring force, is equal to f, the applied force. So it's a force equation. And if you put xt is equal to x e I omega t and ft is equal to f e I omega t into this equation, you are going to get this equation which is written here. So prior to this, the system equation is there, as I am telling you, mx double dot plus kx dot plus mx double dot plus cx dot plus kx is equal to f. That is the system equation. I have replaced xt and ft as x e I omega t and f e I omega t, and I have got this equation. And if you have got this equation, this divided by this is going to cancel out everything, and this is in frequency domain. So you are going to get this FRF, because FRF is nothing but response in frequency domain. So as soon as I have converted xt into x e I omega t and ft into f e I omega t, I have got an equation into frequency domain. Omega is representing frequency. And if I will take the ratio of these two items, I am going to get this expression. This expression is the FRF, frequency response function, for a damped system, single degree of freedom damped system, damped with viscous damping. And if I will replace this viscous with structural damping, I am going to get, these are the FRF curves. Look at this. Now the peak is not, look at this. Now the peak is not very sharp. It is like finite. If it is undamped, it is infinite. It is open, in fact, open from upper side. In graphs, we are not showing infinite because it requires infinite length of the page. But as soon as damping is going to come into picture, it is going to be closed one. It will not be infinite. Similar is the case here. And this vertical line is now a little bit inclined. So these are the changes we are going to see on graphical representation, and these are the things that we are going to see in analytical or mathematical equation. Here we have got one more term, omega c whole square. Earlier with free, we were getting only k minus omega square m whole square root. So square and root cancelled out. So we have got 1 upon k minus omega square m. But after damping, viscous damping, we have got this new factor. So try to remember this formula also. Now, and this formula at every time, if you divide this whole thing by k, you are going to get this. This is a dimensionless version. So either you can use this or you can use this. If you are using this, you will be able to find out damping factors also, along with k and m. Along with, sorry, omega means natural frequencies and mode shapes. Now look at this, structural damping. Minus omega square m as it is earlier, k as it is earlier. In place of c omega, now we have got id. This d is representing structural damping coefficient. C was representing viscous damping coefficient. Again, we have got xei omega t, which is a natural conversion. Every time we are taking xt as xei omega t and ft as fei omega t. Why we are doing it? Because we want to convert time domain system into frequency domain. And once it is converted into frequency domain, we are going to get frequency response functions. Just divide this and this, cancel out this, you are going to get this, which is nothing but frequency response function in a forced damped, structurally damped system with single degree of freedom. So it is a forced system, it is damped, structurally damped, and single degree of freedom. And this is the FRF. Again, if you divide it by k, you are going to get this. And in place of zeta, you are going to get neta. So neta is damping loss factor, structural damping loss factor, and zeta is damping ratio. So that is the only difference. In structural, you have got I neta, and if you look at the back side, the previous one, you have got this c omega, and finally you are getting zeta. So 2I zeta. So that is the difference between viscous and structural. Right now we are talking of single degree of freedom only. So we have got single degree of freedom FRF for forced system without damping, then with damping viscous, with structural. So 3 FRFs we have got. So this is the summary. If you look at this, obviously C is there. So this is viscously damped system, and it can be represented like this. It can be represented like this over. If you look at this H or a small say D is, because here I am using H, it may be represented as D also, small d also. Other things are same. J or I you can use for complex variable, means complex function number. So that is I or J, same thing. H means D. This is for structural part, another way of representing, another way of representing. So this all are same, and all are FRFs. Now, if you look at any book or any research paper, you may get confused, because sometimes they are dividing x by f, they are also dividing x dot by f, they are also dividing x double dot by f. So the first one, this is like receptance x upon f. Now we have got mobility. When velocity is divided by f, this FRF, this is, look at the previous one, what we have calculated till now, displacement divided by f. Now it is velocity divided by f, then it is acceleration divided by f. So if we have viscously damped system and we want to find out velocity divided by f, that FRF is going to be called as mobility FRF. And if we are having acceleration divided by f, this FRF is going to be called as acceleration FRF. So this is acceleration FRF for viscous, this is acceleration FRF for structural. Similarly, this is mobility FRF for viscous, and it is mobility FRF for structural. And if you look at the previous one, this is displacement FRF for structural, and this is displacement FRF for viscous. So there are 3 ways by which we can represent FRF: displacement divided by force, then velocity divided by force, then acceleration divided by force. All these 3 things are available in all the literature, whether it is research literature or book. And if you take reciprocal of this, so when we take reciprocal of alpha omega, the displacement FRF, we will get dynamic stiffness. If we take mobility FRF reciprocal, we are going to get mechanical impedance. And if we take acceleration, this A represent acceleration, this represent velocity FRF, and this represent displacement FRF. So reciprocal of displacement FRF, dynamic stiffness; reciprocal of Mobility FRF or velocity FRF is mechanical impedance, and reciprocal of acceleration FRF is apparent mass. These things are a number of times being used in all research and book related literature. So take care. The modal analysis is not very difficult. Only you must know the jargons. Only you must know the terminology. If you know the FRF, other things can be derived. If displacement FRFs are known, we can go for velocity FRFs, we can go for acceleration FRFs, or in reverse way, if we have got acceleration FRFs, we can go for velocity FRFs, we can go for displacement FRFs, and their reciprocals, we can get dynamic stiffness, we can get mechanical impedance, and we can get apparent mass. Look at here, the response parameter is displacement. You are going to get displacement as response. There are two things in vibration. One is called input, how you are hitting the structure, that is input, and how it is vibrating, that is response. So when the response is in the form of displacement, we are calling it displacement FRF. When it is in the form of velocity, we are calling it mobility FRF. When we are calling it acceleration, when we are getting acceleration as response, we are calling it accelerance or inertance FRF. And the first one is called displacement FRF or receptance FRF or admittance FRF. All these terms are synonymally used in the literature. So don't get confused. And if you take inverse of this, you will get dynamic stiffness, mobility inverse, mechanical impedance, acceleration inertance, apparent mass. Because many times, whenever any person starts doing research, these different words will try to confuse him. So don't get confused. Only one FRF if you are knowing. Other, suppose if you are having acceleration FRF, you can go to velocity, you can go to displacement. And these are their names, standard names: receptance, mobility, inertance, or accelerance. And these are their inverse values: dynamic stiffness, mechanical impedance, and apparent mass. These are the different representation. If you look at the receptance, this is the way. Mobility, this is the way. Acceleration, this is the way. They are all alike, only the value will change. This is the acceleration value, 2. This is the velocity value, say 15, 16. And this is the displacement value, say 40. Another way of representing them, look at this. Generally, when you plot FRF, it's like very small because only one peak is there and other values are very small. So because of that peak, the other values are going to have like negligible value. So generally what people are doing, and that is a standard procedure, they are taking log. And if they are taking log both the side, we are call it log-log plot. If they are taking only log one side at the amplitude side, we are calling linear log plot. It is called FRF dB. dB scale, we are generally calling it dB scale. And this is the formula for that. Look at the FRFs. These are the FRFs when they are being plotted on dB scale. Means you are taking log of the frequency here and you are also taking log of the amplitude. This is receptance, mobility means, and this is inertance or acceleration FRF. After doing experimental analysis using FFT, you are generally getting the FRFs of acceleration type that can be converted into velocity, that can be converted into displacement. And we have to take log of this side also and log of this side also. Why we are doing it? As I told you, generally the peak is so high that the other things are not like visible. You cannot get parameters related to this point, this point, this point, this point, this point. It will become almost horizontal to the x-axis. So that is why we are taking log. Another way of representing these are Nyquist plot. I have already shown you through that 3D figure. These are Nyquist plot. This is for viscous damped system and this is for structurally damped system. Receptance, mobility, accelerance. Receptance, mobility, accelerance. So you are going to get circles. But this is actual circle. This one is the actual circle. Similarly, this is the actual circle. They are not having that circular property. This and this. So just to summarize it, in case of viscous damping, single degree of freedom I am talking about, The mobility FRF possesses circularity. Mobility FRF means velocity divided by force. And in case of hysteretic or structural damping, only receptance FRF possesses circularity. Receptance FRF means displacement FRF. Look at this figure. This is the displacement FRF in case of structural damping, and this is the mobility FRF in case of viscous damping. So try to understand this, that here you are getting circularity, here you are getting circularity, and the center and radius is known to you. Look at this. This circle is having center this and radius this. Similarly, the circle is having center here, radius this. This C is the viscous damping coefficient, and this H or a small d is the structural damping coefficient. So if you know the structural damping coefficient for a single degree of freedom system, you will be able to locate this circle or the FRF, particularly receptance FRF for hysteretic damping and mobility FRF for viscous damping. So these are different properties of FRFs. Otherwise, this is one way of representing them. This is another way of representing them. This is log-log. This is Nyquist. And we are also having like real and imaginary components like this. This is real part. This is imaginary part of receptance, means displacement FRF. This is real and imaginary part of mobility, matlab velocity FRF. This is real and imaginary part of accelerance or inertance, that is acceleration FRF for single degree of freedom system. Now I am switching over to multi-degree of freedom system. Now look at multi-degree of freedom system, means you are having many degrees of freedom. It means now the mass is not single, the stiffness is not single. There are many masses, there are many stiffness, there are many dampers. The worst case is many masses, many stiffness and many dampers. And that is the real case. So here that a small m is replaced by capital M matrix. The small k is replaced by capital K matrix. So this matrix means it comprises of M1, M2, M3, M4, M5, everything and their distribution. Mind it. Whenever I am telling that you have got matrix, it represents both magnitude and distribution both. So you have got mass matrix, you have got stiffness matrix. Again, mass into acceleration with T is inertia force. K multiplied by again X with T means time domain is spring force. And this is the external force. So inertia force plus the spring force is equal to external force. If you are having free system, you will make it 0. And if you want to convert it into frequency domain, you have to replace Ft with the help of F ei omega t and Xt with the help of capital X ei omega t. Let me show you that thing also. But first of all, if suppose it is a free system, then again you are going to get k minus omega square m is equal to 0. Earlier we were getting omega is equal to k by m, which is the natural frequency. Omega square is equal to k by m for single degree of freedom. But if it is a multi-degree of freedom system, the determinant of this is equal to 0 and you are going to get many natural frequencies, omega 1 square, omega 2 square, omega 3 square on the diagonal, omega 4 square, 5 square, omega n square. So all they are placed at diagonal. So these diagonal elements are nothing but the natural frequencies of that system. Suppose it is a 5 degree of freedom system, then the very first element of the diagonal will represent first natural frequency, second element of the diagonal will represent second natural frequency and so on. And related to each natural frequency, we have got mode shape. So this phi 1 vector, this phi 1 vector is the mode vector, mode shape vector related to natural frequency 1. This phi 2 is the mode shape vector related to natural frequency 2 and so on. And you can do it very easily through eigenvalue. If you type in MATLAB eigen, you are going to get natural frequency and mode shapes of any multi-degree of freedom system. Look at this is a say 5 degree of freedom system. This is the mass. M1 is 1, M2 is 1 kg, M3 1 kg, M4 1 kg. This is the stiffness. Here I cannot say that K1 is this much, K2 is this much, K3 is this much. No, K1, K2, K3, K4 is 1000. and this is say K1 plus K2, this is K2, and so on. So this stiffness matrix you are going to get after assembling the elements, and it can easily be done in FEM. So with FEM we are getting the mass matrix, we are getting the stiffness matrix, and through these matrices we are plotting the FRFs, and then we are getting the mode shapes, natural frequencies, and damping factors. So we are getting modal model. So FEM path is also available, analytical path is also available, experimental path is also available. So M and K if given in the question, then this is the basic formula: K minus omega square M phi is equal to 0. And if you directly write eigen within bracket these two values, you will get natural frequencies and you will get mode shapes. So omega 1, omega 2, omega 3, omega 4, I think it's a 1, 2, 3, 4, 4 masses are there. So it's a like 4 degree of freedom system. So with 4 degree of freedom system, we have got 4 natural frequencies, we have got 4 mode shapes. That's it. Look at this. This is first natural frequency, second natural frequency, third natural frequency, fourth natural frequency, and this is the vector. So this vector, this vector, this vector, this vector, if you correlate 0.373 and 604 here, here, yeah. So this is phi 1, this is phi 2, this is phi 3, this is phi 4. Look at this 0.82706. Here also it is 0.82706. So this is fourth mode shape, third mode shape, second mode shape, first mode shape. And this first mode shape is related to omega 1, this one is related to this one is related to third, fourth one is related to fourth. That's it. Now there are some properties, because when we go for multi-degree of freedom system, then the equations are coupled and we have to uncouple them. So to uncouple them, we have to use certain properties also. So this is like in between knowledge piece that must be known to everyone. Look at this. This is phi, this is phi. Phi means mode shapes. Mode shape of rth frequency and mode shape of sth frequency. If you take transpose of this multiplied by M matrix multiplied by the mode shape of sth frequency, you are going to get 0 if R is not equal to S. Similarly, if you replace M by K and again you do this multiplication with transport, you are going to get 0 if R is not equal to S. But if R is equal to S, you are going to get MR and you are going to get KR. These are called modal properties, modal mass and modal stiffness. So these are the orthogonal properties of modes, that if two different mode shapes are being multiplied with M, it is going to result into 0 matrix. But if the same mode shape of same mode is going to be multiplied post and pre-multiplied by M is post and pre-multiplied by mode shapes. Similarly, K is post and pre-multiplied by mode shapes. You are going to get modal mass and you are going to get modal stiffness. These are some properties which we are going to use in coming expressions. Yeah. So similarly, like natural frequency, if you look at K by M, so if KR by MR is divided, these modal mass and modal stiffness is, if we are going to divide, then we are going to get omega R square, the modal natural frequency. So this is these properties are important and they are going to make your equations uncouple later on. I will show you how. Now the second property is, first is orthogonality and second is normalization. Generally the mode shapes which we are getting, they are being scaled. And how they are scaled? The largest element is set to 1 and the other are like reduced accordingly. If suppose the mode shape first element is coming as say 400, so we are making that 400 as 1 and the other we are going to divide it by 400, so automatically it is going to be scaled to 1. This is one way. Many persons, they are like scaling it at different like level. So you can scale it because this is just a shape, so you can scale it up, you can scale it down. If you scale it with the mass, means if you divide the mode shape with respect to the respective modal mass, then they are called mass normalized mode shapes. Look at this. They are represented with psi. So this is the original mode shapes that you have got for rth frequency. If you divide it with under root MR, means root of modal mass related to that rth frequency, then you are going to get mass normalized mode shape for that particular frequency, rth frequency. Earlier we have shown you omega 1, omega 2, omega 3, omega 4 for a 4-degree system. For a 4-degree of freedom system, 4 frequencies are there. For each frequency, we have got mode shape, 4 mode shapes. If those mode shape values are being divided by under root MR, and from where you are going to get MR? From this relation. From this relation, you are going to get MR. So you are getting MR from here, you are getting KR from here, and now that capital M, this capital M is converted into MR. Capital K is converted into KR. So now they are not complete mass or complete stiffness. They are related to, for that particular frequency. So they are related to Rth mode or Sth mode. So for Rth mode mass is this, for Rth mode kV is this. And if you divide this Rth mode shape with respective mass MR under root, you are going to get mass normalized mode shapes. Look at the property. This was the earlier property of orthogonality. Phi Rth means Rth mode, transpose of it, pre-multiplied to M, similarly post multiplied by Rth mode. This is MR. This is earlier one. Now this phi R is converted into under root MR psi R. Similarly, this phi R is converted into under root MR psi R. MR is MR. This multiplied by this, if you look at, you are going to get psi T here, M here, this psi here, and this, because M is cancelled, because this M is, you will get identity property. You both are similarly. We also natural frequencies try to, if you are having more shape. Yeah. जी डॉक्टर अशोक,
हाँ जी सर, कुछ इंटरनेट प्रॉब्लम हो रही थी सर. देयर इज सम इंटरनेट कनेक्टिविटी प्रॉब्लम.
ओहो ओहो, सो यू आर नॉट गेटिंग माय, आप मेरे को ये पीपीटी नहीं देख पा रहे?
आपकी योर पीपीटी वाज विजिबल बट योर वॉइस इज ब्रेकिंग.
Voice is breaking. Okay, okay, okay. So right now is it like,
no you are audible sir. You are audible sir.
Now audible.
Okay sir, now you can,
so let me try again.
Yes you can kindly share your screen sir, kindly.
Right sir. Okay, I'm sorry for that internet part. This is like technical things which are happening. We cannot do anything to these things. This is some issues with online proper this thing, online classes and online system. Yeah, I hope my voice is now like audible and not breaking.
Yes your voice is audible sir. And the screen is also visible.
Okay. Yeah, so like in last few slides what I have shown you, orthogonality property and normalization of mode shape. Orthogonality property, if you look at this, just I will like summarize within 1 minute so that you will be able to recall the previous one. Yeah, if you look at this property, try to remember, and this property here, phi is representing normal modes without normalization. No normalization is done. So if it is for Rth mode and Sth mode, if you pre-multiply, post-multiplied by with M, you are going to get 0 if R is not equal to S. Similarly, you are going to get 0 if R is not equal to S. But if R is equal to S, you are going to get modal mass and modal stiffness. This is orthogonal property. Now normalization, because mode shapes are scaled up or scaled down, you can do anything. So if you scaled it with MR, under root MR, and from where you are going to get under root MR? From this equation. If you are having mass and stiffness matrices, if you are having mass or stiffness matrix, any one of them, you are going to get MR. So if M is available, you can easily convert it into MR, and if KR is available, you can easily convert it into KR. And this MR we are going to use here this MR, under root MR, if you divide this general phi, general mode shapes, you are going to get mass normalized mode shape. These are mass normalized mode shape. And as far as properties are concerned, this is the orthogonality property we have already seen. You replace this thing with the new equation and you are going to get this. So this equation says that if you pre and post multiply with mass normalized mode shapes, mass stiffness matrix ko, if you are going to apply with mass normalized mode shapes, you are going to get identity matrix. And similarly, if K or stiffness matrix is going to be multiplied with mass normalized mode shapes, these, you are going to get natural frequency matrix. So this is another property. If K, if R is equal to S, and if R is not equal to S, you are going to get 0 and 0. But if R is equal to S, you are going to get this. And similarly here also R is equal to S, you are going to get this. Multi-degree of freedom, everybody is knowing. Suppose this is the system given. We have got M, we have got K, we have got C. C means jammed system is there. Multi-degree of freedom because there are many masses, many springs. Generally with the help of independent mass, we will be able to calculate degree of freedom. The mass should be independent. Then you can count them as degree of freedom. If the mass are dependent, then it will count to 1 only. So with the help of independent masses, we will be able to count the degree of freedoms. In a real structure, suppose if this is a real structure, it has got infinite degree of freedom. But infinite natural frequencies we are not interested in. So generally we are taking natural frequency up to say 1000 kilohertz or 2000 kilohertz, the first 10 natural frequencies or first 20 natural frequencies. But actually there are infinite natural frequencies because the structure is infinite degree of freedom. So infinite natural frequencies are going to be estimated. Again, I have done ft is equal to this, xt is equal to this, you are knowing it. So in place of, if you remember the very first, forced undamped, K is replaced by K matrix, M is replaced by M matrix, omega square as it is, X ei omega t as it is, F I omega t as it is. This is under frequency domain. This is forced vibration. This is undamped vibration because there is no C into it. This is after manipulation, after cancelling the X, this ei omega t and ei omega t, you have got this. And if you take reciprocal of these two, means inverse, this inverse is nothing but FRF, frequency response function. And this FRF is of multi-degree of freedom system because K is in the form of matrix, M is in the form of matrix. So they are for multi-degree of freedom, they are for undamped, and these FRFs are receptance FRF, displacement FRF. Try to understand this. That is why I am representing them with alpha omega. That's it. Similarly, if suppose you do that manipulations, what we have done earlier, in place of K, we can go for phi t. K means post multiplying by mode shapes, pre multiplying by mode shapes, then converting them into normalized mode shapes. You are going to get different properties. And after that, like after these manipulations, these are normal mode shapes only. After these manipulations, this is another formula of alpha. This is another formula of alpha. Alpha means FRF, receptance FRF, displacement FRF. If you write it like this, they are mode shapes without anything, means general mode shapes. If you write like this, here the mode shapes are mass normalized. So try to understand the difference between the two. So they are mass normalized, they are normal. So this is another way of writing the same thing. What it shows that in modal analysis, if you are having FRFs, you will be in a position to find out omega r, natural frequency, mode shapes, and if damping is also involved, you will be able to find out damping factors. So you are converting FRFs, you are converting FRFs through modal analysis, you are converting FRFs into, this is the FRF. So you are converting this FRF into this piece, the second piece, and this second piece is omega, natural frequency, and then we have got phi or psi mode shapes. And if damping is also going to present, we may have zeta or we may have neta. Zeta for viscous damp, neta for structurally damp. That is the basic philosophy. Try to remember this part. Whenever you read any book, if you remember this philosophy, FRF is converted into modal model. Modal model means modal parameters. Modal parameters means omega, phi, zeta. This is called modal analysis, theoretical. Again, now this time I have changed. This time I have included damping also. So this is a damped system and viscously damped system. So I'm using C here. And when I'm using C, I have to do certain manipulations. Right now I have taken proportional damping, because damping may be proportional, may be non-proportional. If we take proportional damping, it would be easy for us to uncouple the equation. So we have done this. And once we do this, manipulations are required, and you are going to get this alpha inverse is equal to this. If you correlate this with single degree of freedom, a small k is replaced by capital K, a small c is replaced by capital C, and a small m is replaced by capital M, means matrix M, matrix C, matrix K. Other things are exactly same, no change. These are the FRFs, receptance FRFs, displacement FRFs for a multi-degree of freedom system with viscous damping. That's it. Look here. And now this is one way. So this is one formula which you should remember. So this is FRF formula. Reciprocal of FRF, because here I have written -1. And reciprocal of displacement FRF is nothing but dynamic stiffness. So you may call that this formula is of dynamic stiffness. But if you take 1 upon this, if you take say 1 divided by this whole thing, this will become FRF, displacement FRF. That's it. Now another way to represent it, because right now it is KCM. So if you have a stiffness matrix, damping matrix, and mass matrix, you can get FRF. And if you have FRF, you can get these metrics. So it is that equation. We want modal model also, omega, phi, and zeta. So we have to do certain manipulations. So here we have done certain manipulations, pre-multiplying, post-multiplying, all those manipulations. And at the end, we are getting this. So this is the formula which says that you have got, if you have got this FRF, this is the single FRF. And if you write this, this is FRF matrix, mind it. This is FRF matrix and this is single FRF. This single FRF, if you see, look at, you will get this lambda r, which is nothing but the natural frequency. You have got zeta, which is the damping. You have got the psi, which is the mode shape mass normalized. So you have got psi, you have got zeta, and you have got omega, all related to r. Means rth natural frequency, rth damping factor, and rth mode shape. So this is the beauty of modal analysis, that from FRF you are going to get this, or from this you are going to get FRF. Either way. In experimental, we are measuring the FRF and then converting it into zeta, mode shapes, and omega. And theoretical, we can go reverse also. We have got mass stiffness this, or we have got xi and this, and we can get FRF. But in either way, we are interested in mode shapes, damping factor, and natural frequencies. So this FRF is related to proportional viscous damping of a multi-degree of freedom system, damped system, displacement FRF. And if you take inverse of it, it will become dynamic stiffness. Now in place of viscous, we are using structural damping. Don't feel that it is too much of mathematics. No, it is not that much. Only a single equation is being represented in different form. That's it. Mind it. It is not that difficult. Now this M is as it is, x dot. So this is inertia force. Now capital C is replaced by capital D, and omega is replaced by complex number. So this D is structural damping or static damping. This is damping force. This is a spring force. A small k is replaced by K matrix. So this is for multi-degree of freedom, and this is the applied force. So inertia force, damping force, spring force, applied force. And again, we have taken proportional structural damping. If we take proportional, it is easy to formulate equation. If we take general, little bit more steps are required. That is the only difference. So this is the original equation of the system. Then we have replaced this small x, which is t dependent, into omega dependent. So we have got x e I omega t or j I omega t. F is e j omega t or I omega t. We have got this equation in frequency domain. This is frequency domain equation. And if you look at the manipulation, you will find this as the inverse of FRF. Again, displacement FRF. In case of multi-degree of freedom system, is structurally damped. So 1 upon this is going to give you FRF for a structurally damped multi-degree of freedom system. And directly this formula is going to give you dynamic stiffness. If you want to convert KDM into omega, zeta, or in this case neta and phi, you can do those manipulations, pre-multiplying, post-multiplying, n number of mathematical manipulations here and there, and you are going to get this formula, which is single FRF. This is full FRF and this is single FRF. This is single FRF of a multi-degree of freedom system, is structurally damped, and if this FRF is available, you can get natural frequency omega r, you can get mode shapes, mass normalized or normal, at any point of time you can convert them, and you can get this neta, which is loss factor in case of structural damping. So FRF, or we can say response model, is converted into modal model. That's it, modal analysis. This is analytical way of doing modal analysis. Now try to correlate. I will take I think 5 more minutes to close my session. Try to correlate these representations with single degree of freedom. In case of single degree of freedom, we were getting only single circle like this, only single circle like this, only single circle like this, single one. But this is like multi-degree of freedom. And don't feel only 3 circles are visible. There are many more. But like up to 80 hertz, we have taken 3 or only 3 like frequencies are available. You can increase it to 100, you can increase it to 1000. Generally, all vibration tests are going to end up to 2000 hertz. Generally, up to 2000 hertz, we are closing them. In 2000 hertz, for a given structure, if suppose this is the structure, up to 1000 hertz, you may get 10 natural frequency, you may get 20 natural frequency, you may get 5 natural frequency. It depends on the structure, mass, stiffness, damping, and their distribution. But try to understand that this is the 3D representation of FRF. And if we project them on this screen, if we project them, we are going to get this shape. If we project from the top, we are going to get this shape. And if we project from the side, we are going to get these Iniquity plots. So all the 3 representations can be made through this 3D. Look at this. These are a real and imaginary part of inertance. Inertance means acceleration FRF. X double dot divided by capital F. Capital X double dot divided by capital F. Inertance. So these are shapes are almost same only. So these are real and imaginary part. Go back. Look at this. Look at this. This and this, they are same. And look at this. This line, then this peak, then this line, then this peak. This and this is same. And here you are getting first natural frequency. First natural frequency, say at 100. Say at 200 or 300, you are getting second, and so on. So these represents the natural frequency omega 1, omega 2, omega 3, and so on. Omega 2, omega 3, and so on. And we should always try to load our structure so that such frequency should not match with the applied frequency. As soon as they are going to match, a resonance is going to happen. That's it. These are the Iniquity plot for multi-degree of freedom. Now you are getting two circles. Earlier you were getting a single one. Now you are getting this as well as this. This is for 2 degree of freedom. Even in 3 degree of freedom, you may have overlap circles, you may have little bit shifted circles, and this you are getting from this side. Look at this portion. So this projection gives Iniquity, that projection gives real, and the lower one gets imaginary. So this is a real, this is real, this is imaginary, and this plane Iniquity. These are the different. So at the end, just to recapitulate what I have discussed with you, I have started with modal analysis. In fact, I have started with the issue. Issue was resonance. Then I have started with modern needs. Modern needs says that I want light structure, I want a strong structure, and I want flexible structure. Obviously, if these three things are there, resonance or vibration becomes much more critical whenever you design such structures. Those were the needs. It means modal analysis has to be done. Then I told you modal analysis is nothing but finding out natural frequency, mode shapes, and damping factors. Then I have shown you single degree of freedom mathematics, multi-degree of freedom mathematics. Every time I have finally ended up with frequency response function formula, FRF formula. And I told you, whenever we do mathematical equation analysis, say mx double dot plus kx plus cx dot is equal to f. This is single degree of freedom, forced damped vibrations, viscously damped vibration. Whenever you manipulate this, you will always get displacement FRF, which can be converted into velocity FRF, which can be converted into acceleration FRF. And if you take inverse of them, you will get dynamic stiffness, you will get apparent mass for acceleration, and this thing, the third thing I don't like, I've forgotten, with mobility you are going to get with that yeah, I just forgotten. So three inverse things are going to be there, and these three things I'm just referring that plot. Yeah. Yeah, it's here, inverse. Because that must be, yeah, this one. Mechanical impedance, correct. With mobility, you are going to get mechanical impedance. With normal displacement FRF or receptance FRFs, you are going to get dynamic stiffness. And with acceleration FRFs or inertance FRFs, you are going to get apparent mass. So these are the three things which you should remember. After finding out FRF analytically, those are displacement FRFs. Then you should go for mobility or accelerance. And then you should go for their inverse, and then different representations. The log representation, the Nyquist representation, the real and imaginary representation, and amplitude phase representation. 4 representations are there. One is log or linear log. Second one is amplitude and phase. Third one is real imaginary. Fourth one is Nyquist. So these 4 types of FRF representations are available. 3 types of FRFs are available. 3 types of their inverse are available. Single degree of freedom, multi-degree of freedom is available. Orthogonality property and normalization is available. And when you are going from this side, whenever you are going from this side to this side, it is theoretical route of modal analysis. And whenever you are going from this side to this side, it is experimental route of modal analysis. But in modal analysis, we are always interested in model. Means we are always interested in natural frequencies, mode shapes, and if damping is present, damping factors. This is called a spatial model. This is called response model. Response model means FRFs. If it is frequency domain, they are called FRF. If it is time domain, they are called IRF. A spatial model means M, K, and damping C. And if they are single, you are writing like this. If they are multi, you are writing in matrix form, and you are making them capital. That is the normal notation in any literature. So friends, this is all about the presentation. I have discussed the theoretical part, the basic part. If you have any question, you are most welcome. Otherwise, the coming sessions, they are going to reinforce the same knowledge. They are going to take care of the same thing, because from this multi-degree of freedom, they will develop many more things, and then finally they will enter into experimental modal analysis. And the good part about modal analysis is that complete experimentation is available and you can measure it. Only rotational degree of freedom measurement is little bit difficulty, but translational degree of freedom response you can measure at any point of time. But even if translational degree of freedom measurements are available, you can create the model, you can create the spatial model, and you can create the response model. So this is all about this presentation. I am coming back. I am stopping here. Yeah.
Thank you, Professor Sharad Pradhan sir, for this very informative presentation. So I request to the participants, if you have any query or any doubt or any question regarding the FEM and modal analysis, this session is for the interaction with the expert. So feel free to ask questions. It is my request to all of the participants. If you have any doubt, feel free to ask your doubts, your queries, because this is the interactive session with the expert. Dear student, dear participants,
yeah, if you have any question, definitely this is like mathematically little bit rich and a difficult thing. Even myself, Ashok, and everyone, we have got like at least 6 months to understand these jargons and terminology. So it's difficult, but those who are already doing it, they can ask questions, and those who are starting, they can have like general questions, basic questions.
Hello, good morning, sir.
Yeah, good morning. Please go ahead.
Good morning, sir. Sir, Rahul this side from NITJ Jalandhar, sir.
Okay, Rahul.
So actually, sir, I am.
Rahul, camera on कर लो.
Okay, sir.
Ji, Rahul, yeah. Please.
Yeah, good.
So, sir, actually, I am more of dealing with the experimental model analysis. So I am having doubts in the experimental model analysis since I am joining two metallic materials. So you can also say that I am dealing with the time dependent formula or temperature dependent. Okay, so my question is, sir, whether I can calculate any relation between temperature with the damping?
Temperature with damping?
Yes, sir.
Correct. There are 3 dampings, like viscous damping, frictional damping, and structural damping.
Yes, sir.
Viscous is because of some fluidic around the structure. If suppose a structure is there and some fluid is in vicinity of the structure, maybe air, maybe oil, it is going to come into picture. Structural means the inherent property of the material. And this structural in your case is going to be significant because you are having 2 different materials. So
yes,
once
sir.
the material changes, this structural damping will change.
Okay, sir.
And because like if suppose you take cast iron, the structural damping is high. If you
Yes,
take
sir.
steel, the structural damping is low. So even with the same family members of ferrous family member, with cast iron the damping is high because of the presence of carbon, and with
Yes, sir.
it is. So once you are like combining 2 different things, say metal with resin, obviously the with acrylic plastic type of thing, structural damping is too high.
Okay,
Means
sir.
the curve that we have shown you, the sharp curves, they are going to become blunt, almost blunt like this. And with say steel, they are like this. So
Yes,
this
sir.
is the difference in the damping coefficients. So mind it, structural damping is going to be more critical in your case, number 1. Number 2, if you increase or decrease temperature, definitely the material is going to have different structural damping properties, because once you heat it, it will become little bit soft or hard. I don't know the temperature range in which you are working, but if temperature is going to be there, it will affect particularly a structural part.
Yes, sir. Actually, sorry, sir. Yeah. So actually, sir, I have already read through some paper from the literature review. So there is a temperature dependent of the damping. So with the decrease in temperature, the damping is decreasing, or you can say that it is having a direct relation. For the case of stainless steel or steel material, sir.
Damping is decreasing. Okay.
Yeah.
Correct.
So, sir, my question is, sir, whether which technique I can use to calculate this temperature damping phenomena, like.
Experimental, like there is no issue, because what experimentation you are doing at say 30 degree centigrade,
Yes,
same
sir.
you have to repeat at say 60 degree centigrade.
Okay,
So
sir.
experimentally there will not be any issue. Only you have to create a controlled thermal environment. Because if you are saying that I am placing this complete structure in 60 degree, the complete box should maintain 60 degree throughout the like testing. So
Okay,
as far
sir.
as experimental part is concerned, there will not be any change, because ultimately you are finding out the three parameters, modal
Yes, sir.
parameters, at 30 degree and at 60 degree. But
Okay,
as
sir.
far as analytical part is concerned, or as far as one thing you can do, you can try out the same thing with FEM also,
Yes, sir.
so that you can at least get a validated simulated model. So if you go into FEM, first of all try out with normal ANSYS or normal abacus, and then try to formulate the equations. But
Okay,
in
sir.
that case you have to incorporate temperature also as a derivative. But I think your temperature is constant for that. Means if suppose 30 degree is there, you are going to maintain 30 degree for say 1 hour.
Yes, sir.
Means steady state temperature is there, or it's like varying. Means during testing also it is varying.
Yeah, no, sir. Actually, we are having some material like ambient temperature at room temperature. Then we having a different materials like temperature ranging from 1000 also. So that
Many.
is the concern, sir.
Like applying the temperature. If suppose some material is there, say steel,
Yes, sir.
and you are maintaining say 1000 degree centigrade,
Yes, sir.
and at steady state you are measuring the things,
Oh, yes, sir.
then FEM will do the things, because it is
Okay,
for
sir, okay,
steady
okay.
state, and temperature has time has no effect.
Okay, 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 sir.
Time will not be there. But if suppose during your testing the temperature is changing, then temporal part, time will become another factor.
Yes, yes, yes,
And
sir.
then temporal derivative will come. Then
Yes.
only FEM will not solve the problem. You have to club FDM also along with it.
Yes,
Because
sir.
then the differential equation will be parabolic. And parabolic equation FEM cannot solve. That is
Yes,
the
sir. I got it, sir.
but for that you have to like read literature how to solve parabolic equations.
Yes, sir.
Generally heat flow processes means thermal stresses, but with changing temperature. If suppose a rod is there and you are maintaining it at 1000 degrees centigrade, it is like normal problem.
Yes, sir. Yes, it is
Electrical
normal
electrical differential equation, because temperature is not changing.
Yes, sir. Steady
Once
temperature.
temperature changes with time, then it is very critical, then it will become hyperbolic,
Yes,
and
sir.
then FDM is required along with FEM, because temporal derivative FEM cannot solve.
Yes, sir.
थोड़ा
Thank you so
पढ़ना
much, sir.
पड़ेगा easy. Okay. ठीक है,
Uh,
that's good, great.
Thank you for your question. And thank you, Professor Chandra Pradhan sir. Any other doubt? Dear participants, this session for interaction. So if you have any doubt, please ask, because then if you have any doubt, then you can ask, and then definitely Professor Chandra Pradhan sir will give you a new light on your questions, and so that you can use in your further research for your project and maybe for patent or anywhere. So again, I'm asking, dear participants, if you have any doubt, you can ask me. You can ask Professor Sharad Pradhan sir if you have any doubt.
Okay, I feel there is no question, I suppose.
Actually, I feel, yes, sir, you are right, sir. So I'm very thankful to Professor Sharad Pradhan sir for this lecture, because because this topic is so challenging, as well as a little bit difficult. Not difficult, because first time when you read or when you hear all the words, so it looks like some difficulty in that. But when you use it, then you will feel that it is not difficult, it is easy. And it is very difficult to explain single degree, 2 degree, or a multi degree, and collab with the modal analysis within 1 hour, it is very difficult. But it is your expertise that you are showing here, that yes, it is possible. You explained in a very excellent way, because most of the participants are from inside NIT Jalandhar, and outside participants are also there, and we have also modal analysis facilities also there. And few students are also working on it. Maybe some student wants to work on it. So definitely they will use your guidance and your knowledge, and they will use each and everything in their project work, and definitely they will get the success. So once again, I'm very thankful to Professor Sharad Pradhan sir, for
Thank
this.
you, Ashok. Thanks to you and thanks to Manoj for inviting me and
थैंक्स
giving
डियर
me.
सर,
जी मनोज सर.
आप आए, हम लोग को बहुत अच्छा लगा सर।
जी sir. And thanks for giving this opportunity to interact with persons who are working in FEM and modal analysis.
मनोज सर,
जी सर,
अगर
जी सर, जी सर।
हम ऐसा भी प्लान कर सकते हैं जैसे शरद प्रधान सर इज वर्किंग ऑन अ लॉट ऑफ
सर एक मिनट सर, हाँ जी बोलिए सर, बोलिए सर।
पेटेंट के ऊपर अगर हम सर का कोई लेक्चर ऐसा प्लान कर पाए, क्योंकि
हाँ क्यों नहीं सर, का मेरे पास एक प्रोजेक्ट आया था जो पेटीएम एटीएम के थ्रू जो
Correct. Automatic ration distribution
हाँ,
through ATM.
वो मेरे पास जीएसटी से आया था।
अच्छा अच्छा अच्छा.
जी जी जी
जी
तो मनोज सर ऐसा कुछ प्लान करने का फ्यूचर में सोच सकते हैं।
हाँ क्यों नहीं, क्यों नहीं, ये हम लोग के लिए मतलब रियल लाइफ प्रॉब्लम हो जाएगी,
रियल लाइफ प्रॉब्लम हो जाएगी और लोगों को भी या पार्टिसिपेंट्स को
राइट 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 काफी उस डायरेक्शन में काम कर रहे हैं। तो ये हम लोगों के लिए सर एक तरह से हम एनआईटी जालंधर के स्टूडेंट के लिए और हम लोगों के लिए रिसोर्स हैं। और हम लोग
जब भी आप कहेंगे आई विल बी एबल टू टेल यू द कंप्लीट प्रोसेस।
जी सर, जी
भी
सर।
पता होगा, प्लस प्रोसेस के साथ कुछ जो इश्यूज फेस करता है एक पेटेंट वाला, दैट वी विल आल्सो डिस्कस, क्योंकि स्मूथ पाथ नहीं है कि आपने अप्लाई किया और बहुत अच्छा आइडिया, मैं बोलता हूँ बहुत क्रैकिंग आइडिया है तो भी इट इज नॉट पॉसिबल टू गेट इट लाइक 7 ईयर।
राइट सर,
कि वो 3 साल का तो नॉर्मल पीरियड है।
जी
और
सर।
बड़े सारे इश्यूज आते हैं और रिव्यूअर भी इतने क्रिटिकली इसको रिव्यू करते हैं।
जी
तो
सर, जी सर।
आई कैन शेयर माय एक्सपीरियंस, आई कैन डिस्कस विथ यू,
राइट
शेयर द
सर।
एक्सपीरियंस, नो इश्यूज।
तो वो जो लेक्चर आपका रहेगा ना सर, हम कोशिश करेंगे कि फिजिकल मोड में हो।
हाँ, अब हम लोग इंटरेक्शन जो है
बाकी पार्टिसिपेंट्स रहेंगे जो
एब्सोल्युटली एब्सोल्युटली
उसके बेनिफिट ले पाएंगे और आपसे मिलने का भी मौका मिलेगा सर।
जी सर, जी सर, जी सर।
थैंक यू सर, थैंक्स अ लॉट।
ठीक है, थैंक यू
सर, ओके सर, नमस्कार।
थैंक यू,
बाय
ओके अशोक, थैंक यू।
ओके सर, थैंक यू सर।
सो आई एम लीविंग नाउ, हाँ?
Yes,
Okay, sir.
Thank you, sir. So, dear participants, you can also leave, and please, we will again meet at 2:30 p.m. on the same Google Meet link. So, I will deliver my lecture at 2:30 p.m. So, please join at the same time, please. So, now you can leave. Dear participants, you can leave now.
ओके सर, अभी मैं आ रहा हूँ सर आपके पास।
हाँ जी सर, हाँ जी सर, ओके। Good afternoon, participants. So let us wait for a few minutes so that other participants may also join. So let us wait for a few minutes so that other participants may also join. So I will wait for next 5 minutes. So good afternoon, dear participants. So let us wait. I will wait for 1-2 minutes. Then I will start with my today lecture or on modal analysis of composite structures. Because most of the time when we studied about the composite materials, so or modal analysis, so you can club both of them and find out the resonant frequencies, natural frequencies, eigenvalues and eigenvectors you can find out. And of course you can use the application of modal analysis on composite structures to find out the exact values of the matrix properties or the fiber reinforced properties you can find out. So let us I think I can start. So dear participants, is my voice is audible to you all? Dear participants, is my voice is audible to you all?
Yes, sir.
Okay.
Yes, sir.
Okay. So
Yes, sir.
okay. So also the screen is visible to you all, dear participants. Is the screen is visible to you all?
Yes, sir. Visual.
Okay. Okay. So let us start the today my talk on modal analysis of a composite lamina. So myself, I am Ashok Kumar Baga. I am assistant professor in Department of Mechanical Engineering and NITJ. So these are the different contents, maybe contents of my presentation. First of all, I can talk about the composite material and modal analysis. So most of the time when we talk about the composite material, when we talk about this category like the composite material, and mostly people try to find out its mechanical characterization, like they try to find out the stress strain curves, and they prefer the find out the viscoelastic properties also. But this study, this modal analysis study is also very, very important on it, right? Because it is because in the today morning lecture, Dr. Shard Pradhan sir has already talked about this FRF. He already talked about this FRF. And he also showed that how you can find out the frequency response function of any structure by just finding out the relationship between the output and input, right? So just wait, some participants are joining, so some outside participants are joining. Okay. So this study in terms of composite material is very important, right? So what is this? Right, this modal analysis, right? So most of the time you can use the modal analysis to find out the response of these composite structures of composite materials. How you can find out the response? By putting or mounting the accelerometers, or you can say that you can mount the piezoelectric patches on the composite materials to find out its response. Because in the today lecture also you see that our objective is to find out the response, and response in terms of x divided by f. So this is FRF, and our objective is to find out this response x. Or you can say that your objective is to find out x double dot, right? X double dot, that is the acceleration of the structure, and x dot over f you can also find out that is the accelerance of the system. So if you can use the accelerometers mount on the composite material, you can find out you can find out the acceleration of the structure. So first of all, I will explain to you about the model, this composite material, right? So first of all, you already know about what is the composite material. If I just explain to you about the composite material is a mixture of two materials, right? So two materials mean one material that is a weak material, you can say that is a matrix, and the second material that is going to reinforce it. Most of the time fibers are used to reinforce it. You can see here, this is the matrix. You will see there is a matrix and the fibers are reinforced inside it. You can see and this is a matrix and the fibers are reinforced inside it. And you will see this is a matrix. This is a matrix and the short fibers are reinforced inside it. And you will see this is a matrix and the fibers in terms of particulate, some small circular ellipse type shapes of fibers, you can say the reinforcement. So these are known as these particulate, right? So what happens that when we talk about the composite material, so it is a combination of two materials. One is the weak material in terms of properties, in terms of mechanical property, you can say that, and the another material that is strong enough in terms of properties as compared to the weak material. So when we talk about the weak material, so most of the time plastic is used as a weak material, and the fibers, glass fibers, you can say that, are mostly reinforced in the weak material to improve its mechanical properties in terms of specific strength as well as a specific stiffness, right? So that is why these composite materials are mostly preferred. So there is a various applications of composite materials, and mostly carbon fiber reinforced polymer. So when the carbon fibers, you can reinforce the carbon fiber in polymer you can say that there is a plastic. So when you reinforce it or add the carbon fiber, so this is the strong material in terms of mechanical property, you can say that. Polymer is a weak material when you compare its mechanical properties with the carbon fiber. So when you reinforce carbon fiber in the polymer, the properties may enhance. So there is a different applications. You can mostly industry used this carbon fiber reinforced polymer materials for manufacturing the aeroplanes, the different parts of the aeroplanes like wing, the fuselage, and the landing gears, the power plant, the outer body of the this power plant. They can fabricate it by using the carbon fiber reinforced polymer. And the tennis rackets, you can fabricate the tennis rackets by using the carbon fiber reinforced polymer. The frame of the bicycles you can fabricate by using the carbon fiber reinforced polymer, and the hockey stick, this hockey stick can be fabricated by that. So in the today lecture given by Professor Sharad Pradhan, he talked about when you use any structure, your objective is to make it a light. When you make a structure light, so there is a chance of flexible structure will be there. The structure will be flexible. So when the structure will be flexible, so when there is a small excitation you will apply to the structure will start vibrating. So that kind of problems may occur why you want a light structure. If the structure will be light, so its efficiency can be improved, right? So most of the times when we talk about this aeroplanes, our main objective is to the aeroplane, the weight of the aeroplane should be less, so that its efficiency should be more. So regarding the oil that is used here, the fuel that is used, the consumption of fuel should be less. So like that. So when you talk about the composite material, our objective is to make the structure light. So you can use the glass fiber. So this is the application of the glass fiber reinforced polymers. So when the glass fibers are reinforced in the plastic, so this is the example of the glass fibers. So in the household applications, in the cylinders, in the pipes, and in the helmets, mostly industry is used to fabricate these all parts by using the glass fiber reinforced polymers. So let us talk about the modal analysis, and let us try to apply the application of modal analysis in composites. So first, we can use modal analysis to determine the vibrational characteristics. So today morning also, Professor Sharad Pradhan sir had told that. So why we are studying the modal analysis? Why we are not doing the fluid dynamics and the structural analysis? Why we are not doing? Why we are preferring the modal analysis? Because our primary objective is to find out the natural frequencies damping ratios and the corresponding mode shapes of the structure, because the mode shape pattern is very, very important when we talk about the structural point of view. Of course, natural frequency is an important part, but you cannot neglect the vibrating pattern that is denoted as mode shapes. So one analysis technique for calculating the linear response of the structure to dynamic loading is modal analysis. So you can perform experimental modal analysis to find out the response, either the response in terms of displacement, either the response in terms of velocity, or the response in terms of acceleration. So this is the response you can find out. In modal analysis, we decompose the response of the structure into several vibrating modes. So when we talk about the modal analysis, so we know that when you excite the structure is excited at n number of degrees of freedom, and when it is excited at n degrees of freedom, so n natural frequencies it will be excited. So the response is the combination of the n degrees of freedom. So right, a mode is defined by its frequency and shape. So when you define a particular word mode, so it is defined by a particular frequency, because for a particular frequency there is a definite mode shape is there. So structural engineers call the mode with the shortest frequency the fundamental mode. It can be starting point for another. More detailed dynamic analysis such as transient dynamic analysis, the harmonic response analysis, or a spectrum analysis. So as this lecture, I just want to say that if you want to work on the composite material, or if you are choosing any structure, please initially apply the harmonic response analysis. First of all, apply the harmonic excitation on the structure. So because when you apply the harmonic excitation on the structure, so it means that the excitation is known to you. So accordingly, find out the response. If you are exciting the structure at, let us say that you are exciting the structure at 786 hertz, the response should be at 786 hertz. So you know the exciting frequency, you know the output frequency, then you can say that your FE model is absolutely correct, and you can go for further analysis. So today morning also, this Tacoma, we talked about this Tacoma narrow bridge. This Tacoma narrow bridge collapsed due to the aerodynamic effects. Aerodynamic effects means what happens when they fabricated the bridge and suddenly the air start blowing like this. Suddenly the air start blowing at a particular frequency, right? And what happens that the frequency of this air coincide with the natural frequency of that bridge, and the bridge start vibrating at its different twisting modes, right? So when the bridge start vibrating at its twisting modes, it suddenly collapse and break down because the oscillations of the amplitude are large, and the support system is not sufficient to control it, and it breaks. It breaks due to the twisting modes. There are different kinds of modes in a structure. Either there is a bending modes or there is a twisting modes. So it collapsed due to the twisting of the structure. So this is the example that you can see. If you just type in a YouTube the Tacoma narrow bridge, you will see the example of this kind of bridge. So it collapsed due to the aerodynamic conditions, due to aerodynamic loading, because the natural frequency of the air matches with the natural frequency of the bridge. So it coincide and break down. So let us apply the modal analysis on a composite panel. You can say that by using Abacus software. So this work is done by one of my PhD student, and Rahul Samyal has worked on it. So whatever I will present, all are his observations during his analysis by using the Abacus software. He used Abacus software for that. So composite material are formed by mixing of two or more different materials in homogeneous level that have different properties. Composites are mainly consist of matrix phase and fiber phase. That is a polyester as a matrix and glass as a fibers having orientation. So when you reinforce or when you embed the fibers in the matrix, there is a particular orientation of the fibers. So it can be oriented at 0 degree, 30 degree, 45 degree, 60 degree, and 90 degree. Just wait. Somebody is waiting for somebody is coming in between. Just wait, somebody is coming. I'm just accepting his request. Okay, nobody is here. Sorry for that. So I hope the screen is visible to you all. Right. So So if we talk about the composite material, right? Again, let me take this pointer options. Okay, so is my voice is audible, dear students, participants? I hope my voice is audible. So the fibers can be reinforced in the matrix with different orientation: 0 degree, 30 degree, 45 degree, 60 degree, and 90 degree. So our objective is to find out the natural frequencies and mode shapes when the fibers are oriented at these different orientations. Or one question you can ask with yourself, that is the orientation put any effect on the model of the structure? Is the natural frequency can put an effect on the natural frequency of the system? मतलब अगर हम फाइबर को 0 डिग्री पे ओरिएंट कर रहे हैं, 30 डिग्री पे कर रहे हैं, 45 डिग्री पे कर रहे हैं, 60 डिग्री और 90 डिग्री पे इम्बेंड कर रहे हैं मैट्रिक्स में, तो क्या उसका इफेक्ट नेचुरल फ्रीक्वेंसी पे पड़ रहा है या नहीं पड़ रहा, वो स्टडी हम इसमें करने वाले हैं और वो बताने वाले हैं. So modal analysis is used to determine vibrational characteristics such as mode shapes, natural frequencies, and damping ratios. Modal analysis can be done experimentally or by using different simulation software such as MATLAB, ANSYS, NISA, Abacus, and many more. Yesterday, Professor U.S. Dixit has talked about it, and he told that you can use MATLAB, ANSYS, NISA, Abacus, or any software you can opt to do the finite element modeling or analysis by using those softwares. So maybe you can further use the application of modal analysis to find out the optimal location of a sensor. So it is a location where there is no nodal line coinciding with the sensor location. So this is very, very important term, that is optimal location. This term is very, very important. So when you use any software, so let us say that you are using a backup software and you want to model, you want to make the finite element model of a composite panel. So there is a need to give some inputs. The inputs in terms of modulus of elasticities of the fiber as well as the matrix. The inputs in terms of the shear modulus, of the input in terms of the Poisson's ratio, the inputs in terms of the density, and the dimensions of the beam, the length, width, as well as the thickness and the mesh size, right? So these are the inputs that are required when you are using any software. It means that you are inputting the dimensions, you are putting the boundary conditions, and you are inputting the material properties of the structure when you model anything. So when you are more focused on the modal analysis, the most important property is the density. So please put exact value of the density, because when you put the exact value of the density, then without applying any force, because when you are doing the modal analysis by software, do not apply any kind of a force. By using the density itself, it will start vibrating and it will act as a force and start vibrating, and will provide you the natural frequency of different system, right? So the fibers can be reinforced in the matrix in a 0 degree. So you will see the fibers are 0 degree. The fibers can be reinforced in the 45 degree. So this is 45 degree. The fibers can be reinforced in the 60 degree direction, right? And the fibers can be reinforced in the 90 degrees. So these are the different orientations in which the fibers are reinforced in the matrix, right? And our objective is to see what happens when the fibers are oriented at 0 degree. What is the natural frequency of the system? So when the fibers are oriented at 45 degree, what is the natural frequency of the system? When the fibers are oriented at 60 degree, what is its effect on the natural frequency of the system? And again, when the fibers are oriented 90 degree, what it puts effect on the natural frequency as well as on the mode shape of the system. So that thing we want to find out. So that is our objective, is to find out, because when you fabricate the composite material, there is a weight fraction as well as the volume fraction. So please try to take constant volume fraction, right? So let us say that there is a 90% matrix is there and 10% fibers is there, right? And the total is 100. So our objective is to find out the natural frequency when the fibers are oriented at different direction. So this is the first of all, when I know that you all are the researchers and maybe you are doing very well work in your field, in your college or in your industry, but the first most important thing is the validation. Please validate your research with some previously published paper. So that is very, very important. So in this case also, if you see there is a reference paper is there. So this is the reference paper. So the natural frequency is provided there as well as the material properties are also there. So you will use all these properties and try to make the model in Abacus and compare the natural frequencies And you will see these are the natural frequencies. This is the first fundamental natural frequency.
So thoda slow.
Hanji?
So little bit slow when you are delivering that very fast. So your voice is overlapping and it will not come clearly.
Okay. Maybe due to some internet
Network lag.
Yes. There may be a network lagging. Thank you. I will take care of this and I will move slowly. Thank you for your this opinion. Okay, so you will see this is the first fundamental frequency. This is the fundamental frequency 121.11 hertz. The units should be mentioned there. It should be hertz, right? And you will see according to this first fundamental frequency, the beam is vibrating like this. It is a composite beam. I have already shown you the properties of the composite beam. It is fixed from here. It is fixed from here. It is fixed from here. And you will see that the beam is vibrating like this. The beam is vibrating like this. So it means that during the first fundamental mode, all the mass of the beam either move in the plus direction. Let us say that this is plus direction, or it will move in the minus direction. You can say like this, right? And this is and you will see during the first mode there is no nodal point is here. Nodal point is a point where the response of the structure is approximately 0. So at the second fundamental frequency 773.35 hertz. So this is the second mode shape of the composite beam, or the composite beam, you can say that. In this case, you will see here, this is the maximum response is here. This red color shows the maximum response. And here you will see a blue color. Blue color means where the response is approximately 0. So this is the point you will see here where there is no amplitude of the beam, and this blue color shows that the amplitude is approximately 0 when the structure is vibrating at this particular fundamental frequency. So again, when you see the third fundamental frequency 2 to 5.1 hertz. So you will see these are the two nodal points are here. One is here and the second one is here, where the amplitude of the beam is approximately 0. So it means that in these two positions the beam is not vibrating. You can see that. At fourth fundamental frequency, at this fundamental frequency, again you will see the beam is clamped from here. It is a cantilever beam, right? Now this is the nodal point, this is the nodal point, and this is the nodal point. So these are the nodal points, those points where the response of the beam is approximately 0. So what kind of information you are getting here? So you are getting information, first information you are getting about the frequency, and the second you are getting the mode shape. Let us say that the mode shape vector is represented by a phi. Let us say that. So you are getting the information about the mode shapes. How you can use this information? You can use this information of this mode shapes and say that these are the nodal points. These are the nodal points, right? So these are the nodal points. It means that when your objective is to measure the response of the cantilever beam, never mount the accelerometer at this point. Never mount the accelerometer at this point. Never mount the accelerometer at this point. Never mount the accelerometer at these points. Because if you will mount the accelerometer at these points, the accelerometer will not sense the contribution of this mode, because you are putting the accelerometer at the nodal point of the second mode. So the accelerometer will not record the contribution of the second mode. Of course, the same if you will mount the accelerometer at these 2 points, the accelerometer will not sense the contribution of the third mode. Again, if you will mount the accelerometer at these points, again what happens? The accelerometer will not sense the contribution of the mode number 4. So it means that whatever you are recording the half information. You are not getting the complete information, right? If you are doing the modal analysis, the information should be complete enough. The information should be complete enough. So this is the advantage of natural frequencies as well as mode shapes. That is why mode shapes are very, very important when you are doing the modal analysis. So this is the example of the cantilever beam. You can say that it is a one-dimensional structure. You can say that. Let us talk about a composite lamina. or a plate. We know that a composite plate or a lamina is a two-dimensional. Why it is a two-dimensional? The third dimension, the thickness is very, very small. And when you use any Abacus software or any software, there is a need to do some input in the software in terms of mechanical properties, right? Density, modulus of elasticity, in terms of dimensions, like, and in terms of boundary conditions. So these three inputs are provided by you when you are using any kind of a software: the dimensions, the boundary condition, and the material elastic properties, right? So the fibers again can be reinforced in 0 degree, 30 degree, 45 degree, 60 degree, and 90 degree. So these are the different orientations of the fibers that can be reinforced in the matrix, right? So number of elements. So in this study, 3D shell feature is selected with planar type. So my PhD student used this, right? So you can divide that plate into finite number of parts. You can divide any 12 by 12, 15 by 15, any you can divide into finite number of parts, right? So this is the modeling in Abacus. You can use Abacus, and I already told you when you are using Abacus or any software, there is a need to put some inputs in terms of mechanical properties. So these all are the mechanical properties. You can say that mechanical properties. Shear modulus is, there is a need to put shear modulus, right? So these are the shear modulus and Poisson's ratio and density also. So there's a density, right? So there is a need to put all these things. So let us take the example. Now what happens that, so this slide is very, very important, because this slide is very, very important. This slide tells us, let us say that the boundary condition of the plate is a simply spotted. It is simply spotted from all the edges. Let us say that the plate is simply spotted from all the edges, right? And you are doing the modal analysis. So when you are using Abacus, there is a direct function is there, modal analysis. So you can use that direct function to find out the natural frequency. So this is the natural frequency, first fundamental natural frequency, and this is the corresponding mode shape. This is the corresponding mode shape. So you will see when the structure is simply spotted from all sides. So the first fundamental frequency is 1.49 Hertz, and this is the mode shape, right? So the maximum displacement is at the center, and at the boundary, the displacement is less. Blue color shows the less value of the displacement as compared to the red one. So the second fundamental frequency is 3.80 Hertz, and you will see a nodal line at the center. You will see a nodal line at the center. It means that this is the line that represents that the value of the response or the displacement is approximately 0. You just correlate with the blue color. The blue color represents the less value or a minimum value, and the red shows the highest value or the maximum value. So when again you will see here there is a misconception is here. You will see that these two frequencies are same, 3.80, 3.80, but the mode shape is different. But the mode shape is different. So it is a square plate. So what happens that either you can pick this or this, both are same, because it's a square plate. So you are getting a nodal line at the center. Again, you are getting the nodal line at the center, right? So these two frequencies are close, or you should pick a one frequency. Or you should choose. If you will pick 3.80, either this mode will be happen or this mode will be happen. There is no confusion in that, right? But when you perform experimental study, then you can say that either this mode is the correct one or this mode will be the correct one. So you can choose it by doing the experimental testing. So this is the mode number 4 at this frequency, 6.07 Hertz. So how many nodal lines? So there are 2 nodal lines. So this is the nodal line 1. This is the nodal line 2. So these are the 2 nodal lines are here. So you will see here in the first mode, there is no nodal line. In the second mode, there is a 1 node line. In the third mode, you can say that there are the 2 nodal lines. So when you will increase the frequency, you will see these are the nodal lines, looks like this. These are the nodal lines, right? Again, when you will increase the frequency, so you will see, you will see this nodal lines are looks like this, right? So this is a different pattern of vibrating and again you will see here both the frequencies are same. These two frequencies are absolutely same. So which frequency is correct? So when you will perform the experiment according to the particular mode shape, you can say that this frequency is the correct and this frequency is according to this frequency, this mode shape is incorrect. So you can say that you can choose by doing the experimental study. For clamped boundary condition. So again, the clamped mean the plate is clamped from all the sides. So this is the fundamental frequency. This is the mode shape. This is the second fundamental frequency. There is a one nodal line. This is the third fundamental frequency, and you will see there is a nodal line. This is the fourth fundamental frequency, and there is a nodal line, right? So the one interesting thing you will see here, so when the boundary condition is simply spotted, the first fundamental frequency is 1.49 Hertz. But when you change the boundary condition, so when you change the boundary condition, it means that you are adding some stiffness, because when you add some stiffness, the natural frequency should increase. So when you say that the plate is clamped from all the side, the frequency is increasing. It increasing from 1.49 to 2.74 Hertz. So for each mode, the frequency is continuously increasing. So it means that when you change the boundary condition, the natural frequency will also change, right? So this is the boundary condition when the plate is free from all the sides. So this particular boundary condition represents the boundary condition of an aeroplane. So when the aeroplane is moving, so there is no boundary condition on it. So it is moving as a free, right? So this free boundary condition, replica of the boundary condition that is applied on the aeroplane, and you will see this for this fundamental frequency. So this is the nodal line pattern. So this is the nodal line pattern. So this is the nodal line pattern, and you will see this frequency is very, very close to zero. You can say that. So when you talk about the free system, so it means that there is no boundary condition on the plate. The first few fundamental frequencies are close to zero. So it means that the structure is working as a rigid body like aeroplane. You can say that. And again, for a particular degree of freedom, there is a particular mode shape and the particular pattern of the nodal line. So again, here you will see here, this is the nodal line pattern, and this is the mode shape corresponding like that. So this is the cantilever case also. When the plate is cantilever, it is cantilever, it is fixed from one edge. There are the four edges of the plate. So it is fixed at one edge and the other edges are free. So it is a cantilever, you can say that. Again, you will see for this first fundamental frequency, this is the mode shape. So second fundamental frequency, this is the mode shape. Third fundamental frequency, this is the third mode shape. So why this slide is here and what is the advantage of this slide is, so for all the possible boundary conditions, you will observe that the natural frequency is not same for all the boundary conditions for a composite plate, and the mode shape is also different. So when the plate is simply spotted, the mode shape is different. When the plate is clamped, mode shape is different. When the plate is free condition, the mode shape is different. When the plate is cantilever type, the mode shape is different. It means that the modal analysis by using the software like Abacus, it is possible to fabricate, it is possible to make a model of the matrix and fiber reinforced inside it, and then doing the modal analysis easily on it by using the softwares like that, right? So this slide represents that when the plate is clamped boundary condition. So this slide is also very, very important slide. For research point of view, you can say that there is a great importance of this slide. If you are doing research in these areas like composites, modal analysis, FEM, vibration, acoustics, noise, so this slide is very, very important, right? Because, so let us say that FO means fiber orientation, right? So this is the matrix, neat matrix. Neat matrix mean there is no fiber reinforced inside it. There is no fiber reinforced inside it. So these are the different modes: mode number 1, mode number 2, mode number 3, mode number 4, mode number 5, and mode number 6, right? So when there is no fiber reinforced inside the matrix, so it is a polyester, you can say that. So this is the first fundamental frequency and this is the corresponding mode shape. This is the second fundamental frequency and this is the corresponding mode shape with the one nodal line. This is the third mode shape. You can say that fourth mode shape, fifth mode shape, and you can say that this is the sixth mode shape. So there are total 6 modes you will be observed here, right? So what happens? So our objective is what happens when the fibers are reinforced inside the matrix with a particular fiber orientation. What its effect? So you will see a huge effect here. So for the neat matrix, the frequency is 2.74, and when you add a matrix and when you add a fiber in the matrix, the frequency changes from 2.74 to 65 hertz. So it means that because due to the Young's modulus difference between the fibers and the matrix, that is why this difference is here, right? And you will see here when the fibers are oriented at 0 degree and 90 degree, these are the fundamental frequencies. Right? And this is the corresponding mode shapes. So let us compare the mode shape. The first mode shape of the matrix and the first mode shape when the fibers are oriented 0 degree and 90 degrees same. The second and third mode shapes are same. Fourth mode is same. But the fifth mode, you will see in the fifth mode in the neat matrix, you will see there is a cross sign is here. But when you see the mode shape of fifth mode shape of fiber oriented 0 degree 90 degree, you will see vertical lines like this. Right? So this is the advantage of these softwares, that it will directly tell you the mode shapes. Now if you just compare these two mode shapes, so when you will compare these two mode shapes, so you will see that the pattern of the nodal lines is changing continuously, right? So it means that when you are using an accelerometer, so you cannot mount the accelerometer at the nodal lines, right? So let us say that unfortunately you say that the vibrational pattern may be same, and unfortunately you mount the accelerometer here. So what happens that this accelerometer location will definitely take the contribution of this mode, but it will not take the contribution of this mode that belongs to the matrix, because you are mounting the accelerometer at the nodal lines of the matrix. तो जब हम मैट्रिक्स का मॉडल एनालिसिस करेंगे, उसका फिफ्थ मोड आप कैप्चर नहीं कर पाएंगे, लेकिन वही एक्सेलेरोमीटर अगर आपने उसी लोकेशन पे यहाँ पे लगाया और वो 0 डिग्री और 90 डिग्री पे जब फाइबर होंगे तो उसका कंट्रीब्यूशन वो ले लेगा. तो ठीक है, तो ये हमें पता चल रहा है. नाउ वी आर गेटिंग द एडवांटेज of the mode shapes when the fibers are reinforced in different orientation. So let us the fibers are oriented in this degree, 30 degree and 60 degree. Mostly fibers are oriented when you belong the shear stress, when you want to resist the shear stress, the fibers are oriented 45 degree. So now you can see, let us compare these two cases. Now you will see here in this case, this is the nodal line when the fibers are oriented at 0 degree, 90 degree. But now the nodal line is changing to this. The diagonal nodal line is observing here. So it means that these two pictures gives us a very information, right? Very qualitative information we are getting here, that you cannot mount the accelerometer at this nodal line. You cannot mount the accelerometer at this nodal line. So now again you will see this is the nodal line pattern, but now the nodal line is again a diagonal pattern is here. So here you will see that nodal line will make a plus sign, right? Here the nodal line is not making a plus sign. There are two nodal lines, those are diagonal in nature, is completely seen to us. It means that it is completely visible that the importance of the nodal lines. Because what is the importance of nodal line? The importance of nodal line is that it gives us information that please avoid the accelerometers to put on the nodal lines. If you will put the accelerometers on the nodal line, they will not give you the complete information about the vibrational structure of the system. The dynamics of the structure you cannot completely extract doing the modal analysis, because you never mount the accelerometer on the nodal line, never. So it means that if you will compare these pictures, so it is clearly visible to you that there is a great importance of the modal analysis in composites, right? Because maybe in the industry is not doing those kind of modal analysis, and blindly they say that, okay, when the fibers are oriented in 0 degree or when the fibers are oriented in the 45 degree, they will not put any effect on the dynamic characteristics of the structure. So you will say, you will see a very, you can say with a confident, no, the orientation, the effect, the fiber orientation put its effect on the natural frequency, because here the natural frequency is 194 and here the natural frequency is 188. So there is a difference in the natural frequencies, right? Either the boundary condition is same, however, there is a difference in the fiber orientation. So it means that the fiber orientation put its direct effect on the natural frequency as well as on the mode shapes of the structure. So this is very, very important. Again, for different boundary conditions, you will see here. So maybe these cases you can use for different. You can use this. You can use for different cases. But of course, I also just want to discuss with you one case, right? I will not take so much time of you. I just want to take a case so that you can correlate with today's lecture with that. In today, Professor Shraddha Pradhan sir told about you this, the model, the prediction of a model. So what is model? You can find out the model by solving the eigenvalue problem. By solving the eigenvalue problem, you can find out the model. So eigenvalue problem means you can find out the eigenvalues or eigenvector. So basically this equation in today morning, Pradhan sir was told about that the stiffness matrix, the mass matrix, and the mode shape matrix, you can say that. And you in the MATLAB, how you can find out the natural frequencies and mode shapes? By using the MATLAB, there is a command, EIG command, you can use to find out the natural frequencies and the mode shapes of the structure, right? So today morning also it is discussed with you. Let us say that there is an equation of motion, the inertia force as well as a spring force. There is no damper, let us say that. And already we told you that, let us say that the harmonic force, a force is acting on the structure. If the force is harmonic in nature, the response will also harmonic on nature. So when you find out x dot and x double dot and put here, so you will reach up to this equation. This is the frequency response function that is abbreviated with alpha omega x by f, right? So 1 over k minus omega square mg. So today morning, Dr. Shraddha Pradhan was focusing on that. By using this relationship, you just vary the value of omega, and you know the K matrix and M matrix. You vary the value of omega from 0 radian to 100 or 1000 radian per second and plot the value of alpha. So when you are modeling with some softwares or you are modeling with some packaging, I have already told you, you require some material properties, material dimensions, as well as the fiber orientation. So each and everything should be required to you. You can use that, right? So by using MATLAB or by using any MATLAB, you can find out the mode shapes as well as the natural frequency. So this work is also done by my MTech student. The work is already published. Again, you will see when the fibers are oriented, different orientation like 0 degree, 15 degree, 30 degree, there is a change in the natural frequency. There is a change in the natural frequency as well as the corresponding mode shapes. So it means that the orientation put its effect on the natural frequency of the system. So again, in today morning, Dr. Shraddha Pradhan has showed you the FRF. So by solving the eigenvalue problem or by using the EIG command or by solving this value, so today morning he showed you this value. Again, I will show you here this alpha he showed you today. So there is a great advantage of this. You just solve it with different values of omega. You know the K matrix and M matrix. You can plot the frequency response function curve. You can plot this frequency response function curve. On x-axis there is a frequency. On y-axis there is a FRF in dB, decibel. And today morning he told you why you plot in dB, because if you will not plot in dB, the importance of the vibration modes whose value is small will be not shown in a linear scale. So you will see there are different types of frequencies are here, and corresponding to each frequency. So this is the first fundamental frequency, second fundamental frequency. According to the peaks, you can find out the natural frequencies of the system, right? And again, there is a MATLAB command LSIM. There is a MATLAB command LSIM command you can use there is a MATLAB LSIM command you can use. There is a very important command. There is a LSIM command you can use. There is a LSIM command is used, because when you are using MATLAB, you are trying to solve the partial differential equations by making your own MATLAB code. But if you want to plot in a time domain, you can use LSIM command. And if you want to plot in a frequency domain, there is a command FREQRESP. So this command you can use to plot it, right, in a frequency domain, and LSIM command you can use to plot the response in the time domain. So these are the different plots. You can plot it. So why I am showing you this? Because my objective is to convey to you how you can use the modal analysis, right? So in this slide also, you can opt the modal analysis way to find out the mode shapes, take the advantage of the mode shapes, and represent it. There is another very good application of modal analysis is also very famous. That is the direct updating method, or different updating methods are also there. So what you will do in the updating methods, let us say that there is a composite laminar structure, right? There is a simulated model or there is an experimental model, let us say that. So in the simulation model, there are errors, maybe error in the boundary condition, in the material properties, or in the dimension. But the experimental model is an error-free model. It will give you actual results. You can make the mathematical model. You can make the mathematical model of the structure. You can get the natural frequencies and eigenvalues of experimental directly. You can compare both. So you can compare both. So when you compare both, you will see an error. Find the difference, because experimental results will never match with your simulated results. Or you can say that there is always a difference between the simulated results and experimental results, right? There's always an error. So you can remove that error. You can remove that error or uncertainty by using the direct updating method. So this direct updating method will give you the opportunity. This updating method will give you the advantage. So you can use that method, and then by using this method, you can update the mass matrix and stiffness matrix of the structure. You can update the mass matrix and the stiffness matrix of the simulated model, and then you can use that method to compare your simulated results with the experimental one. So this is also the great advantage of the modal analysis, that how you can use the modal analysis to improve the simulated finite element model, because we are talking about FEM. So FEM is a numerical tool that gives us approximations. It never gives us the exact result, right? Because it works on the approximation. The approximation may be the material properties, the dimensions, and the boundary condition. So always it works on the approximations. So it's a numerical tool that solves the partial differential equation, you can say that. So it will not give us the actual results. So but maybe you are using the FEM model to control the vibration of the structure or control the noise, etc. So there is a need of actual structure. Actual FE model should be required. A correct FE model should be required. So you can improve that FE model by using the experimental data, and there is a technique that is a direct updating method is used. So this is the direct updating method. You can use this direct updating method. It will update the stiffness matrix as well as the mass matrix by using the experimental data. एक्सपेरिमेंटल डाटा का यूज करते हुए ये आपका स्टिफनेस और मास मैट्रिक्स को अपडेट कर देगा, और आपका जो सिमुलेटेड मॉडल, जो एफई मॉडल है आपका, वो एग्जैक्ट हो जाएगा, करेक्ट हो जाएगा. उसकी नेचुरल फ्रिक्वेंसीज, उसकी जो ऑब्जर्वेशंस है और जो एक्सपेरिमेंटल ऑब्जर्वेशंस है, उनमें एरर कम हो जाएगा, दोनों मैच कर जाएंगे, बोथ विल बी मैच. सो देयर इज अ टेक्निक. There is a technique that is very well developed in the literature. There is technique is known as a direct updating algorithm. तो इसे direct updating algorithm का नाम बोला जाता है. So I think it is sufficient for today. So from I will not focusing more on that. So today I told you that about the how you can apply the modal analysis and composite structure, and there is a great advantage of modal analysis for composite like structures. So maybe it is useful, because let us take a simple example. Let us say that I told you that for a particular boundary condition there is a corresponding mode shape, and the structure is vibrating accordingly, right? So when the structure is vibrating accordingly, maybe due to the different fiber orientation, the radiation of sound is different, right? So by using the modal analysis, first you can find out the mode shape. According to mode shape, you can find out the nodal lines. According to the nodal lines, you can see the behavior, what happens to the sound radiation when the sound will be radiated for a particular type of orientation. So it will give you the idea about the sound efficiency also, sound radiation efficiency also. Can we use this application for in terms of acoustics or noise? So that is why the modal analysis, because modal analysis is nothing. Modal analysis is either there is experimental route or a theoretical route that Adhanshu told you today. Either you can opt any route, either simulated route or experimental route, but your objective is same. Your objective is to find out the model. Your objective is to find out the natural frequencies, corresponding mode shapes and damping ratios. That is your main objective to find out it, right? So how you can find out? Either you will FEM, because most of the time you are using FEM, either you are using Abacus, ANSYS, or write your own MATLAB code, right? So or you are using experimental route. So maybe sometimes the structures are very simple, then you can opt the experimental route. But let us say that the structure is a complicated one, and it is very difficult to mount the accelerometer on that structure. So then you will go forward with your simulation models and try to make the simulated model of that and find out the model of the structure. So there is a way. So today morning also told you there is a way to move further, right? First of all, you make the mathematical model of the structure, writing the equation of motion, assume some forces, assume the response, right? And then apply some input excitation, you will get a response, right? So when you will get a response, let us say that you get the response in the frequency domain. So by using that response, you can find out the natural frequencies and mode shifts you can find out. And during experimental way, so what you will do, let us say that there is a cantilever beam. You just mount the accelerometer here, and this is the fixed point of the cantilever beam, or fixed end of the cantilever beam. So when you excite the cantilever beam from here, it will start vibrating like that, right? And then you can, there's a accelerometer is mounted here. The accelerometer give you will say one signal. It will record one signal, and the part of this accelerometer may be attached with the CRO, and the CRO will be give you information about that, and you can use that information to find out the model and other things. So I think it is sufficient for today. So today I told you about the composite material, the application of modal analysis of composite material, the advantage or the effect of fiber orientation on the model of the composite material. So there is a great advantage of that. So if you have any doubt, dear students, participants, I think it is sufficient for today for this expert talk. So if you have any doubt, you can ask me. Dear participants, if you have any doubt, you can ask me. Dear participants, if you have any doubt, you can ask me. Okay, so if you have no doubt, I'm just going to request you one thing. So tomorrow there is an expert talk by Professor S.V. Modal. He is the father, or you can say that he's the godfather of modal analysis, because in India, only one institute, IIT Delhi, is working on this modal analysis mostly. And then NITJ is also working on that, but not at that scale. The Modal Surgery is working on that. So it is very fortunate to hear something from him. So because when we are studying in NITs or any state colleges, so we dream to hear some IIT professors. So it is a great opportunity for all of us to hear something from him, right, in terms of modal analysis, right? So I just request to all the participants, tomorrow the lecture will be start at 9:50 a.m. So please available before 9:50, and he will deliver his lecture maybe for for 1.5 hours. And after his lecture, importance for us, right? And after, because like if you will present, then there is a use of this STC. Otherwise, there is no advantage of this STC. We will also put a message in the group also regarding the tomorrow talk. So if you have any doubt, participants, if you have any doubt, you can ask me. Dear participants, कोई doubt है आपको? पूछ लीजिए. Dear participants, if you have any doubt, you can ask me. Okay, so I think what I...
Excuse me, sir. Excuse me, sir. Sir, we have seen some problems on plates also, sir, like this what you have told. But till now, I have not done any problems related to shells, cylindrical shells or conical shells or hyperbolic shells. Next class or something.
Okay, sir, definitely I will note down and definitely we will try to do it, definitely. And
Okay, sir. Thank you. Thanks.
okay, participants, I think it is sufficient for today. So if you have any doubt or questions regarding, you can also put in the group also. You can also put in the group also, because the person is asking something and his voice is not clear. So you can put your query in the group also. There is a group is also there. You can put your query. And maybe in future also we are going to organize one FDP or some workshop on patents, how you can move for patents, how you can use that advantage of patents, how you can process your files. So definitely Dr. Sharad Pradhan sir will definitely join when we arrange that FTP. So definitely we will again come back to you. So okay, participants, I think it is sufficient for today. So you can leave, but please present tomorrow definitely, right? So good afternoon, and you can leave.